joint work with Alistair and Daniel Kane about learning multivariate log concave distributions. Specifically, we're interested in the sample complexity, and we give the first upper bound on the sample complexity of learning log concave distributions in arbitrary dimensions. Previously, the only upper bounds that were known were for 1 to 3 dimensions. So generally, we need to assume that distributions have some structure to learn them. One simple way of specifying structure is by shape restrictions on the probability density function. So we might have a probability density function that's monotone or bimodal, or in the case we're interested in, the logarithm of the probability density function is concave. The problem of learning under shape restrictions has been well studied, with work going back to the 50s. It's still a active research area. The statisticians tend to first analyze the maximum likelihood estimator. The problem we're interested in is density estimation. We want to learn a distribution to within epsilon total variational distance, and we'd like to be robust against model misspecification. And the two goals keep in mind the number of samples we need and the time we need for the algorithm. And here we're concentrating only on the sample complexity. So as I said, a log concave density is one where the logarithm of the probability density function is concave. And this includes many familiar distributions and has nice compositional properties. So much of the prior work on this only applies in one dimension. There's work on the beta convergence of the maximum likelihood estimator. And there's also been work in the probable theoretical computer science perspective, where they look at other algorithms that are sample and computationally efficient. In more than one dimension, it's been known for a while that the maximum likelihood estimator is consistent. We take enough samples, it eventually converges. And the most relevant recent work for us is work by this paper by Kim and Samworth, which considers, again, they consider the maximum likelihood estimator under Hellinger distance, and they give tight upper bounds on the number of samples needed on 1 to 3 dimensions. And they also give a lower bound valid in any dimension of 1 over epsilon to the d plus 1 over 2. Now our result is that we give a bound of 1 over epsilon to d plus 5 over 2. So this is exponential dimension. It's only really feasible in low dimensions. And this is within a factor of 1 over epsilon squared of the known lower bound. This doesn't use the maximum likelihood estimator. Indeed, it's going to be it's more robust than the maximum likelihood estimator would be. And the general approach is we're going to find a class of functions which can approximate any log concave function. And if we have this, we can we can learn this with an algorithm that only considers the probability that the set of the sets where one of these approximating functions is bigger than another. Now, if this family of sets has a small VC dimension, then we can take a few samples, and by the VC inequality, now we only need to look at the empirical probabilities of such sets. And we only need a few samples to get those close. This approach has been considered recently in 1 dimensions for various classes of distributions, including log concave distributions. And you usually get good sample complexity and efficient algorithms. So yeah, this is a log concave function. And we want to find an approximate. We're going to approximate this by a piecewise constant function. The way we're going to do this is we're going to take a finite number of relatively closely spaced levels, and we're interested in super level sets where the probability density function is at least something. And then we can define our approximation by this piecewise continuous approximation by, for every point, we consider the highest of these super level sets that the point is in. And that will give you the value. Now, if you look at two of these and look at the set where one is bigger than the other, it's going to be a union of intervals. And that has small VC dimension. In higher dimensions, now if we look at the super level sets, they're like these things are like contours of the probability density function. The super level sets are nested convex sets. Now, yeah, we don't know the VC dimension of a general convex set, so what we have to do is to do more approximation. We're going to approximate these with convex polytopes. And then our approximating function is going to be defined with these convex polytopes. We're going to take the value of a point to be the one of these approximate super level sets with the highest probability, corresponding to the highest probability density function that it's in. And from here, the idea of the proof is relatively simple. So by standard results in convex geometry, we can approximate an arbitrary convex body on the inside, but within an epsilon fraction of its volume, using 1 over epsilon to the d minus 1 over 2. The convex polytope with 1 over epsilon to d minus 1 over 2 faces. So this convex polytope is the intersection of 1 over epsilon to the d minus 1 over 2 half spaces. It's well known what the VC dimension of the family of the set of half spaces is. In d dimensions, it's d plus 1. So now, if you look at the set where one of these piecewise constant approximations is bigger than the other, it's going to be a union and intersection, the difference of all the half spaces involved. Now, if we have d over epsilon levels, then we have d over epsilon to the d plus 1 over 2 different half spaces. And if we do some counting, we can get the VC dimension is also going to be about the same, d over epsilon to d plus 1 over 2. And this immediately gives that the sample complexity is d over epsilon to the d plus 5 over 2. Now, we don't even give a bound on the time complexity of this algorithm. So the obvious open question is there a computationally efficient algorithm with this time complexity? The maximum likelihood estimator is still a good candidate. It has a simple expression as a convex program, but we haven't actually got bounds on its sample complexity. So is this the optimal? Well, it is to within a factor of 1 over epsilon squared, but that makes a difference in low dimension. Now, this VC dimension idea was quite fruitful in one dimension. It applied to many different things in local K distributions, so can we do that in high dimension? Thank you for listening.
Questions? Okay. Sir?
So what happens to, this is only local and not mixture of this, right?
Yeah, not mixtures.
So you give the translation of mixture.
No, we didn't.
Can you repeat the question?
We could probably use it. So he was asking about mixtures of log concave distributions. No, we didn't consider that, although you imagine that we can also approximate those with piecewise constants. And so there's going to be, we can probably get some result using this method, but no, we didn't consider that.
Okay. Yeah.
So your estimator is piecewise constant on nested polytopes.
Yes.
But the MLE is almost the same, but instead of being piecewise constant, it's piecewise
linear, yes.
So So have you tried actually to do the same analysis instead of spacing your locomotive function by piecewise constant function?
So yeah, so the big difference with the maximum likelihood estimator is that it's piecewise linear, yes, but it's kind of it's like we consider a convex set with a convex polytope which is defined with few vertices. And the VC dimension, we don't know the VC dimension of that. We only know if it has few faces, and that's the difficult part of the analysis. So we don't know how to analyze things that look like the MLE in the same way.
Okay. Let's thank the speaker again.